properties of bituminous mixtures used for pavement design. The presentation is designed as follows. We will talk about various modulus, then we will talk on the tests or the experiments carried out at IIT Madras as a part of the DST project. Then I will show you some interesting analysis, some results we obtained, and we will go for the discussion. I will take all the questions towards the end of the session. We all know that a typical pavement structure consists of 4 to 5 layers, of which the top 2 layers are made of bituminous materials and the bottom layers are made of granular materials, all of which lying on the top of a compacted subgrade. And the bituminous mixtures or the materials exhibit a viscoelastic response. That is, the response is dependent on the temperature as well as the frequency of loading. By frequency of loading, I mean the speed of the vehicles plying on the pavement. For example, the response of the material to a 40 km/h vehicle will be completely different from that to a 100 km/h vehicle. Coming to the importance of material property or material modulus. This is a very important property which is used as an input parameter in the stress analysis stage of any pavement design procedure. To carry out a stress analysis, it is always better to model the full pavement structure wherein we can integrate the material properties over various layers as we do in finite element software such as Abacus and COMSOL. Since most of the pavement design softwares we have use linearized elasticity based stress analysis procedure, we have to input something like E and U, that is elastic modulus and Poisson's ratio, to characterize the materials used in each layer. Then how will we characterize the frequency dependent nature of a material? For that we use some surrogate modulus or some substitute modulus which we use in place of elastic modulus. The most commonly used surrogate modulus are flexural modulus, dynamic modulus and resilient modulus, all of which we will be going to discuss further. So, here comes the overview of various modulus, and the first one is the flexural modulus, and this is conducted as per ASH 2 T321 2007. In this we use a beam sample, rectangular beam sample of 380 mm long and 63 mm width and 50 mm height, and the sample is loaded by means of 2 inner clamps and 2 outer clamps, and this material is subjected to sinusoidal loading by means of an actuator which applies load from the bottom, and the central deflection in the beam is measured by means of a probe or an LVDT mounted at the middle of the sample, and the sample is loaded in such a way that the middle 1/3 portion of the beam is subjected to pure bending, and we conduct the test at 0, 10 and 20 degrees. You have to note that this test cannot be conducted at higher temperatures because the beam fails by sagging, and we conduct the test at 10 Hz frequency which simulates a vehicle speed of about 64 km/h, and from the applied load and the measured deformation, that is central deflection, we can calculate the tensile stress and tensile strain using the equations which are given in the ASH2 protocol, where P is the load applied, B is the width of the beam, H is the height of the beam, delta is the central deflection, L is the length between the outer clamps and A is the length between the inner clamps. And we define flexural modulus or stiffness modulus as they call in the standard as the ratio of the tensile stress to the tensile strain. Okay, let us move on to the next modulus, which is the dynamic modulus, which is one of the most commonly used modulus, and the test is conducted as per ASH2 TP 79 2010, and in this we use a cylindrical sample of 100 mm diameter and 150 mm height, and the sample is subjected to Haversine compression loading. You can see the actuator here applies a compression loading, and the test is conducted across 10 frequencies starting from 25 Hz all down to 0.01 Hz. So, 25, 20, 10, 5, 2, 1, 0.5, 0.2, 0.1 and 0.01 Hz, and the test can be conducted from 0 to 60 degrees Celsius. We know the load is applied from the bottom, and the resulting deformations are measured using 3 LVDTs which are fixed 120 degrees apart. This is the test setup, and we know that this is the load waveform and the epsilon is the strain and we know that the strain lags the stress by delta, which is the phase angle, and dynamic modulus is defined as the ratio of the peak stress to the peak strain values. Okay, now let us go to the next modulus, which is the resilient modulus. And in this test we use a cylindrical sample, 150 mm dia and 63 mm thick sample, and the sample is subjected to Halogen compression loading across the periphery, that is the material is loaded across the vertical diametral plane of the sample, and the test is generally conducted at 1 Hz, that is we apply load for 0.1 second duration and we give a rest period for 0.9 second duration, and this goes on, this is repeated, and this is the resultant deformation or the strain. We can see that during loading the strain increases, and during the rest period the accumulated strain in the material starts recovering. The recovery can be divided into two portions. One is the instantaneous recovery and one is the one which is time dependent, that is which goes till the end of the cycle. So, at the end of the cycle we can have epsilon r, which is the recoverable strain, and epsilon p, which is the plastic strain, or we call it a permanent strain. And the resilient modulus is defined as the ratio of repeated axial stress to the recoverable axial strain. Since we have two types of recovery, two types of recoverable strains, we can have two resilient modulus. One is total resilient modulus and one is the instantaneous resilient modulus. As a part of the DST project, we have characterized the material based on both dynamic modulus test and resilient modulus test, and our discussion further will be confined to these two tests. And let me explain the test in detail. As already discussed, the test is conducted on a 100 mm diameter sample by 150 mm height, and we apply Halogen compression loading, and the test at IITM was conducted at 6 temperatures, 5, 15, 25, 35, 45 and 55 degrees Celsius. We used two types of mixes, one is BC and one is DBM grade 2, and we used 4 binders, one unmodified VG30 binder and with modifiers, that is CRMB 60, PMB plastoma 40, PMB elastoma 40, and all the samples were fabricated at 4% air voids, and we used the shear compactor, press box shear compactor for fabricating the sample, and we cored this size samples from the press box beam. And let me explain how the test is conducted or the procedure. At a specific temperature, a cylindrical sample is subjected to frequencies from 25 Hz all down to 0.01 Hz continuously without giving any rest period between individual frequency runs, and the average strain to be maintained throughout the test was fixed as 75 to 125 microstrains, and it was assumed that within this strain range the material response is always limited to the linear viscoelastic regime. So, at the start of the test we input a seed modulus or an initial modulus into the software, equipment software, and the software computes the load required to maintain the strain within this range, 75 to 125 microstrain range, and it applies 5 conditioning cycles. Then next 5 conditioning cycles are applied if you want to readjust the load levels, followed by 10 test cycles. Okay. From the equipment software we get the data only for the test cycle. The conditioning cycle data is generally not available from the equipment software. Then using the procedure mentioned in the AASHTO protocol, we calculate dynamic modulus using regression procedures. Now let me show you some of the results, interesting results we obtained in our laboratory. This is for BC grade 2. You can see that at 5 degrees the dynamic modulus value is higher, and the dynamic modulus is seen increasing with increase in the frequency and decreasing with increase in the temperature. So, at 5 degrees we have maximum dynamic modulus, whereas at 55 we have the least. The same trend is obtained for all the other binders also. Like you can see for plastoma, with frequency modulus is increasing and with temperature it is seen decreasing. The same trend is also obtained for all the other binders, and here are the results for DBM. Here also the trend exhibited is almost the same. This first one is for VG30, plastoma, CRMB and PMB. let's come to something interesting. Let's compare between the binders. That's what we all want. We can see that at 5 degrees Celsius, the triangle one is the plastomer. The plastomer modified binder has the highest dynamic modulus, followed by this Vg30, followed by elastomer, followed by CRMB. The order is written here. We can see that this unmodified binder is seen having higher modulus than the modified binders at 5 degrees, which is a low temperature. But we can see that as the temperature keeps increasing, the order is also changing. PMB plastomer, followed by elastomer, followed by Vg30, CRMB. CRMB is having the least dynamic modulus of all the 4. But let's see what happens at 55 degrees. You can see that all the modified binders have higher modulus than our unmodified Vg30 binder. These are the results for dBm. This also the trend is the same. That's at lower temperature you can see Vg30 has higher modulus, whereas at higher temperatures all the modified binders are seen having higher dynamic modulus than unmodified binder. Coming to the master curve. So in the laboratory we conduct the test over a very small range of temperature. We said 0 to 60 and over a small range of frequencies. But in the actual payment design, we may want the modulus value at some other combination of temperature and frequency. So what will we do? How will we go about? It will be always very advantageous if we can shift the dynamic modulus across the temperatures and across the frequencies, and if we get one single curve which covers a wider range of temperatures and frequencies. Such a curve is called a master curve, which is obtained by plotting reduced frequency along the x-axis and the dynamic modulus along the y-axis, both plotted in a log-log scale. For example, if you want the dynamic modulus say at 6 Hertz at some temperature 68 degrees, what will you do? You will calculate the reduced frequency from the frequency. That's our frequency is 6 Hertz. We will calculate reduced frequency using some shift factor. The shift factor takes into account the temperature we need, and from this curve we can get what is the dynamic modulus required. That's how we use the master curve plot. And it's always advantageous to compare the binders based on the master curve, because we can get the complete trend of the material, response of the material over a wide frequency range. You can see that the frequency range is from 10 to the minus power 12 and 10 to the power minus 12 to 10 to the power 12. And across all the frequency range, plastomer has shown higher dynamic modulus value followed by elastomer. We can see that over lower frequencies, CRMB has higher modulus than Vg30, whereas at higher frequencies Vg30 has more dynamic modulus than crumb rubber modified binder. So let's move on to the next testing, that is the resilient modulus test. And there are 2 standards available for resilient modulus testing. One is the withdrawn standard ASTM-D 4123 and ASTM-D 7369, which is the revised standard. The table shows the comparison between the 2 standards. And the first difference is in the test setup. In the withdrawn standard, we mount LVDTs only in the horizontal direction. That is, we can measure only the horizontal deformations. The vertical deformation is not measured. So Poisson's ratio always has to be assumed. Whereas in the revised protocol, that is ASTM-D 7369, we have LVDTs mounted both in the vertical as well as the horizontal directions. And the advantage is that we can always compute a Poisson's ratio at different temperatures of testing. And the other thing is the LVDT gauge length. Here we can see that the gauge covers the whole diameter of the specimen, whereas we have a choice of selecting the gauge length for the revised protocol. And the gauge length can be 1/4, 1/2, 3/4 and full diameter of the specimen. And it's to be noted that the resilient modulus changes with the gauge length. And coming to the sample dimensions, these are the sample dimensions. Generally we can use a 100 mm dia sample or 150 mm dia sample. For IITM testing we used 150 mm dia sample with 63 mm, 63 plus or minus 0.5 mm thickness. And the sample surface in the old protocol they don't recommend anything, but whereas in the new protocol they say that the sample is to be polished, it has to be sawed. This has a very important effect, it contributes in the calculation of the resilience modulus. Then coming to the test parameters. So, what is the input load that should be given before starting the test? The old standard, withdrawn standard, tell that you conduct an IDT test, that is a failure test, indirect tension test, where you load the sample to the failure, capture the failure load, calculate 10 to 50%, take one value and use it as the input in the next test, that is our resilient modulus test. But whereas in the revised protocol D7369, they ask us to take 10 to 20% of the load from the ITS test. And as I told you, the load duration is 0.1 seconds followed by a rest period of 0.9 seconds. And the test temperature is fixed as 25 seconds. The code says conduct the test at 25 degrees Celsius. But at IITM, we have conducted the test at 20, 25, 30 and 35 degrees Celsius. And this is the test setup. The sample, as I told you, 150 mm. This is the diameter and the thickness is 63 mm. We have LVDTs mounted on both the planes, both horizontal and LVDT, and we apply Haversine compression loading. The actuator is here. And this is the procedure what we do. We conduct an IDT test, indirect tension test at 25 degrees, and 10 to 20% varies with the binder used. For plastomer, we will take 1% loading. Elastomer, it is different. So, we choose, it is all based on trial and error, how it works. And for example, we keep the sample in this orientation. Say this is 0 degrees. We apply 100 cycles of loading, 0.1 second loading, 0.9 second rest period. Like that, 100 pulses are applied. We capture both vertical as well as horizontal deformations in the sample. Then what we do is we give some rest period for the sample. We have tested it for 100 cycles, so let's give it some rest period for some 15 to 20 minutes. Then we rotate the sample by 90 degrees and again we follow the same thing. That is, we again apply 100 cycles, capture vertical and horizontal deformations in both the planes of the sample. So let's see what we get after the test. Before getting into that, let me show you how we do the post-processing of the data. The blue line, the blue one shows the load pulse and the red one is the deformation pulse. For post-processing, the ASTM standard suggests that the recovery portion is split into 3 parts, 1, 2 and 3, and fit a straight line to the portion and 2 hyperbolas to this second and third portion. And why do we want to do this? Because we want to know what is the instantaneous deformation, recoverable deformation, and what is the total recoverable deformations. And they tell us extrapolate the straight line, draw a tangent at T55, which is sometimes specified in the ASTM standard, which is around 0.59, and the meeting point just extrapolated to the curve, and this is taken as the instantaneous recoverable deformation used for the computation of resilient modulus. And similarly, we have total resilient modulus. How will we calculate that? So, we have to find total recoverable deformation. We take the average of deformation at TE and TF, which is 0.855 seconds and 0.956 seconds. So, the deformation at these times, we take the average and we find the total recoverable deformations. And from that, there is a procedure in the ASTM standard. You may please refer to ASTM D7369, and we calculate Poisson's ratio as well as resilient modulus. So, from the test, we get 8 modulus for each sample, because we have 2 planes, then we have 2 rotations, then we have 2 types of recoverable deformation. So, we have 2 into 2 into 2, that is 8 modulus for each sample, and they ask us to do the test for 3 replicates. So, in a total we have 24 resilient modulus value, and the ASTM standard does not give a precise precision and bias statement. They say that the within laboratory repeatability is to be 7% based on 1 laboratory, 3 test replicates and 6 different samples. They do not say what is the repeatability between the planes, between the rotations, and also they do not give the reproducibility of the test. And also the standard says that this should not be used for acceptance or rejectance of the material for purchasing purpose. And let us see some of the results what we obtained, and we can see that at 20 degrees, plastomer has the highest resilient modulus, followed by elastomer, VG30 and CRMB. But and also at 25 we find the same trend. But at 35 degrees we can see that all the modified binders have higher resilient modulus than VG30. Still VG30 is having the lowest resilient modulus. And this is a table I have taken from IRC 37, and we can see, for example, at 30 degrees for VG30 we have 5500 MPa as resilient modulus. but here we can say at 30 degrees we have 2500, which is almost half of the value which we get using our protocol. This may be because this IRC was, this table was prepared using D4123, the old withdrawn standard, and where you use the full gauge length for testing, and we have used half the gauge length. So I told you resilient modulus depends on the gauge length. That may be the reason for the difference in the values in IRC table as well as using the new protocol what we conducted here. And now it's time to compare between two tests. We have resilient modulus, we have dynamic modulus. So we have to make some conclusions. So here are the results. We can see that at 25 degrees, always you can see that resilient modulus is higher than dynamic modulus. It may be because you have a rest period during the resilient modulus test. We are giving 0.9 seconds as rest period. So the strains will be substantially low. So the modulus will be substantially high for resilient modulus when compared to the dynamic modulus. That trend is seen for all the mixtures at all the temperatures. But however, we can see that at 25 degrees VG30 is having higher resilient modulus and dynamic modulus than CRMB, whereas at 35 degrees when the temperature increases, all the modified binders have higher resilient and dynamic modulus than the unmodified binder. So coming to some conclusions or discussions, we have two test methods, both are different, sample geometry, everything are different, so which one to choose? So how will we decide upon? Dynamic modulus covers a wide range of temperatures and frequencies, 25 Hz to 0.01 and temperatures from 0 to 60. And the repeatability criteria is well defined and the test is very fast. We can complete the test in about 1 hour. Whereas in resilient modulus, we can't conduct the test at 40 degrees because the sample fails. We have tried testing it, but we couldn't test it at 40 degrees with substantial loading. Even with 6% loading, we had to put so much effort to get some value, some decent results. And the frequency range is limited. The standard says test at 1 Hz, or you can also use 0.33 and 0.5, but they don't recommend anything more than that. And also we have 25 modulus values, so which one to choose is also not yet finalized. So we think that dynamic modulus would be a better representative of how to characterize the material. I would like to acknowledge DST for the funding given and also IPC Global for the continuous technical support provided to us. Thank you all.